The first step one needs to take in order to develop a control system is to clearly understand the system we want to control. In this lecture, we are going to create dynamic models to represent plants or processes for which a control system will be developed. To that end, we use two sets of models for mechanical and electrical systems, and eventually we'll be able to combine them. We're going to start with a model of simple elements such as masses, springs, and dampers, and then we'll combine them to form more complex systems and see how we can describe the dynamic behavior of both electric and dynamic systems, and then see the connection between them. By the end of this lecture, you should be able to clearly see the relation between a mechanical and an electrical system. As you'll see, they are described by the same set of differential equations. We should be able to model mechanical and electrical systems and then find the differential equations in the time domain that represents them. Let's start our study with a mechanical system. In any mechanical system, there will be a mass, and the mass is what quantifies the amount of matter in a body. We are all familiar with this concept. If you apply a force to a mass, that will make the mass accelerate. Here, if you have a mass called m, and you apply a force f of t to that mass, that will result in the acceleration and the displacement of the mass. If F is the force applied to the mass and x is the displacement, we can now create a relation between these two quantities by applying Newton's law. The sum of all forces equals to the mass times the acceleration. In terms of displacement, we can now write the sum of all forces, which in this case is simply F of t, equals to the mass times the second derivative of displacement, that is dx squared dt squared. The second derivative of displacement with respect to time. We are going to use in this course the following notation. A derivative will be represented by a dot, a second derivative by a double dot. So you can write that f of t equals to m, the mass, times the acceleration as a function of x, the displacement, that is x double dot, where again x double dot is the second derivative of x with respect to time. Now let's consider a similar system, but instead of a linear system, let's consider a rotational system. Instead of applying a force, we apply a torque. And instead of having a linear displacement, we have an angular displacement that we're going to call here theta1, and tau being the torque. The same way we had the mass that would oppose any changes in motion in the linear system, in the rotational system we have the moment of inertia. We're going to call here J. The equation of motion for this system now is the sum of torques is going to be equal to the moment of inertia times the angular acceleration alpha. The sum of all torques acting on this system here is simply tau of t, and alpha is the second derivative of the angular position theta of t. And according to our new notation, we can write tau of t equals to j theta double dot, where again theta double dot is the second derivative of theta with respect to time t. The next mechanical element that we need to study is something able to store energy in the form of potential energy, and that will be a spring. When you have a spring element, the assumption is that we are only dealing with a mechanical system that stores energy in the form of potential energy. That is to say that there is no energy dissipation, there is no damping in the spring, and the spring has no mass. For a system that has both a mass and a spring, we now need to combine a spring and a mass that we saw before. Now we can relate the force developed in the spring and the displacement of the spring. We know that the force in an elastic element is equal to its compression or its stretch times the stiffness constant that we are going to call here K. Let's assume, for instance, that on one end of this spring we have a displacement x2, and the position on the other end of the spring is x1. So the total compression or stretch of that spring will be x2 minus x1, provided that a force is applied at the point where x2 is. We can now write that the force developed in that spring is the stiffness constant K times the compression of the spring, that is x2 minus x1, where K is the stiffness constant given in newtons per meter. Again, if you fix one end of this spring and apply a force to the other end, this side here we have x2 and this side here we have x1, which in this case is 0. But if that end is also allowed to move, then you need to consider the relative compression or stretch of that spring, that is x2 minus x1. This is for a linear spring. If we now look at a torsion spring, we can say that the sum of all torques applied to the spring, tau of t, is equal to the angular stiffness multiplied by the relative angular displacement of the spring, that is theta 2 minus theta 1, where K in this case is the angular stiffness, that is Newton meter per radian. If you multiply Newton meter per radian with radians here, we get Newton meter, which is the unit for torque. The next element we need is something that is able to dissipate energy. And to this end, we are going to use a viscous damper. We're going to use the same idealization as we did for the spring. If you're now dealing with a viscous damper or an element that is able to dissipate energy, we are going to assume that this damper has no stiffness and has no mass. Think about a viscous damper as a damper in a car, for instance. If you press on a damper slowly, you feel a small force, but if you now press fast, that force increases. We can then say that the force developed in a damper depends on the speed that that damper moves and on the magnitude of the viscous friction coefficient B. This graph here represents the developed force. The force increases linearly with the velocity, and the slope of this curve is the viscous friction coefficient. Now, do not mix viscous damper and dry friction. Viscous damper is a form of friction, but it's not dry friction. The curve that we see here is the traditional curve that we use to model dry friction in a mechanical system. We see that this is very nonlinear, which cannot be used in control systems because the assumption we made in lecture 1 is that everything is linear. We need to assume that the force developed in this element is proportional to the speed. We can think about it as an element that dissipates energy, such as a damper in a car, or we can also think about the contact between two surfaces. Viscous friction, for instance, between a mass and a plane. If the mass moves, the faster it moves, the greater the resistance against that motion comes from friction. And this friction, again, increases linearly with the velocity, and it is not the same as dry friction. We can say that the force developed in this element is proportional to the speed of both ends of that element. That proportionality constant is B, that is the viscous friction coefficient, and the net speed across that element is the speed of one end, that is x2, the position of one end, so the speed is the first derivative of that, minus x1 dot, the speed on the other end of that element. And according to our notation again, x dot is dx over dt, which is simply the speed. If you now look at a translational system, instead of force we have a torque, we still have a coefficient of viscous friction, but now we have an angular velocity on one end, that is theta 2 dot, and on the other end we have theta 1 dot. And this is now the force developed in a translational viscous damper. The unit for the viscous friction coefficient is Newton second per meter, and for the rotational system is Newton meter per second. And again, notice that this curve for static or dry friction depends on the position, whereas here we are dealing with speed. Now that we have the basic elements that we can use to model any mechanical system, we can attempt to describe the motion of this mass spring damper system here. Let's neglect gravity for now. We have this mass is subjected to a force F of t, and we have a damper and a spring holding that mass in place. The graph on the left is one representation of the viscous friction. The graph in the center is the same representation. In the center, we see that there is viscous friction between the mass and the sliding plane, which is the same as connecting the mass to a damper to a fixed reference frame. These two formulations are exactly the same. If you want now to find the equations of motion for this mass spring damper system, let's start with a free body diagram. Here we have a mass. We have one external force applied to it, that is F of t. And if the mass moves downwards, then both the damper and the spring will apply a force against motion, and that force will then be upwards. If you now call the displacement of this mass x of t, we can write the magnitude of the spring and damper forces. If the mass moves by x, then the spring applies a force k times x. If x is the displacement, then x dot is the speed, and the damping will be b, coefficient of viscous friction, times x dot. This is the free body diagram. Now we need to create a convention for the sign of forces. Because the external force is pointing downwards and the mass is accelerating downwards, let's assume that everything in that direction is positive. Now we can write the sum of all forces acting on this mass equals to mass times acceleration, or mass times x double dot. We have three forces acting on this mass now. The first one is F of t, is positive because it points down. And we have the viscous friction, that is negative bx dot, it points up, so it's negative, minus kx, the spring force, again negative because it points up. And this is equal to mx double dot. We can now rearrange this equation as mx double dot plus bx dot plus kx equals to f of t. And this is a differential equation that describes the motion of this mass when subjected to a force F of t. Now let's move on to electric elements. In electric systems, there are three main linear components that we will need throughout this course. The first one is a resistor, the second one is a capacitor, and the third is an inductor. You are all well familiar with these concepts, but let's revise them here briefly. The resistor is an element that dissipates energy in the form of heat. We're going to consider that a resistor is a purely resistive load. It has no inductance and no capacitance. If a current I passes through that resistor, that creates a voltage drop V. And that voltage drop V is the voltage V1 on one end of that resistor minus the voltage V2, the voltage at the other end of that resistor, V1 being higher than V2. And this is equal to the current times the resistance R. The voltage drop across a capacitor is also V1 minus V2. The assumption when you have a capacitor is that there is no inductance and no resistance. We have a purely capacitive load. We can now write that this voltage drop is 1 over C times the integral of the current, integral of I dt. If you reverse this equation, we can say that the current in the capacitor I is C times the derivative of the voltage. Looking at this equation, we can see, for instance, that if the voltage is DC, is a continuous voltage, dV dt is 0, the current through a capacitor in a DC circuit is 0. The last element is an inductor. The voltage across the inductor is also V1 minus V2. And let's assume that we have again a current I going through that inductor. The assumption is that the inductor element has no capacitance and no resistance. The voltage drop across it as a function of the current is L times the derivative of the current. Notice from this equation that in DC, di dt is 0, and there is no voltage drop across the inductor. In a DC circuit, the inductor behaves as a closed circuit as a short circuit. We can also revert this equation and write now the relation between I and V as I being the integral of V dt times 1 over L. Now that we have all the electric elements we need, we can try to find the equation for this circuit here that has a LRC circuit and a voltage V. We are interested in the relation between the voltage and the current and the voltage and the charge in the circuit. The current we're going to call it I, and the charge we can call it K. Let's start with the current. If we apply a voltage to this circuit, there is a current developed. Now applying Kirchhoff's law, we know that the sum of all voltages here is 0. Because the potential in this source here is positive and negative, and all other potentials are positive and negative in the opposite direction like that, we know that a negative V plus the voltage across the capacitor plus the voltage across the resistor plus the voltage across the inductor is 0. So you can write that V is the sum of all voltage drops, starting with the capacitor, that is 1 over C integral of I dt. The voltage drop across the resistor is R times I, and the voltage drop across the inductor is L di dt. Again, this is simple Kirchhoff's law. This is the first expression. This relates the voltage and the current. If you're now interested in the relation between the charge and the voltage, we need to relate the charge and the current first. If you call the charge Q, we know that the charge is the integral of the current, so integral of I dt, which gives the current as the first derivative of the charge as a function of time. We can now replace this expression we just obtained in the first one and now relate the voltage and the charge directly. V becomes 1 over C times the integral of I. I, in this case, now as a function of the charge, is dq dt plus I times R. I is dq dt times R plus L times the derivative of I. So I is dq dt. The derivative of dq dt is d squared q dt squared, the second derivative of the charge. If you rearrange this equation now, we have V equals to the integral and the derivative cancel. We have 1 over C times Q plus dq dt, according to our convention, that is Q dot times R, plus L Q double dot. So here is the relation between charge and voltage, and here is the relation between current and voltage. Now let's take this analysis one step further, and let's see if you find any analogy, any similarities between the mechanical and the electrical system. And you'll see this is quite interesting. Let's go back to our mechanical system where we apply the force F of t and watch the displacement x. And let's look at our electrical system again, where the input was a voltage and the output was the current or the charge. These are the equations that we found in the previous example for the mechanical and electrical system. We see here that they follow the exact same structure. The variable of interest in one is x, the displacement, and in two is the charge q. The external excitation was the force and the voltage. So the force and the voltage are analogous. They are the elements that are being applied to the system to create a change in the states of that system. We see this term here multiplied by the second derivative of the variable of the interest, the mass and the inductance. We can say that as the mass stores energy in the form of kinetic energy, the inductance stores energy in the form of a magnetic field. Those are the elements storing energy in the system. Moving on, we see B and R being multiplied by the first derivative of our states here, x and q. While in the first, the viscous damping dissipates energy in the form of heat, so does R in the electric system. It dissipates energy in the form of heat. So the viscous friction coefficient and the resistor are analogous. They are both there to dissipate energy. The last element that we see is K and 1 over C. They are also analogous. They represent the compliance of the system, how susceptible the system is to move, or how easy it is to develop a charge in the electric system. This represents, again, the compliance in the system. We can clearly see that these two equations are the same. They follow the same structure. If we now solve for these two differential equations for a given set of M, B, K, L, R, and C, the time response to an impulse will follow this expression for both systems. The impulse response represents the initial condition in the system, and you let the system go from the initial state. For instance, we can assume that there was an initial compression in the spring, we moved the mass, held it, and then let it go. Or there is an initial charge in the capacitor or initial current in the inductor, and you let the electric system go from there. Another way to think about an impulse response is to give the system a very short impulse, a very short excitation, such as we slap the mass and let it move from that state, or turn on and off the circuit very fast. To summarize this discussion, this is the analogy that we can make now between an electric and a mechanical system. The force is analogous to voltage, because those again are the elements applied to the system that will make them change from one state to another. The velocity is equivalent to the current. The displacement is equivalent to the charge. Notice that the displacement and velocity are related. Velocity is the derivative of displacement. Notice that current is the derivative of charge. Damping is equivalent to the resistance. They both dissipate energy. Mass is equivalent to the inductance. They both store energy. And 1 over K is equivalent to the capacitance. That's the compliance of the system, or how easy it is to make it move or establish a current or a charge in an electric circuit. Let's see if we can understand this analogy with a simple example here. I'm taking random values for M, K, and B, and also for RC and L. And you're going to analyze here the step and impulse response. Let's start with the mechanical system, and let's start with a step response. Applying a step to the system means apply a force and holding that force as time tends to infinity. If I plot the force applied here, this is time and this is f of t, the force goes from 0 to a given value and is held constant as time tends to infinity. In other words, we apply the force to the mass, we stretch the spring, and when the force we are applying is the same as the spring force, then the system stops moving, and then you hold that force still. Now what happens? If we do that, if we apply a step input to the mass will start to move. It will have some inertia because of the kinetic energy in the mass. The spring and the damper are holding it back. And at the point where the force we apply and the reactive forces due to the damper and spring balance out, the mass stops moving. It first oscillates because of inertia. Those oscillations are eventually damped out because of this damper. And at the end, when the oscillations stop, the system reaches equilibrium, and will reach equilibrium at a given position. So we'll see this curve in the time response if you watch the displacement of the mass. Now let's look at the electric system. Instead of applying a force, we now apply a voltage. Applying a step voltage to this circuit means turning the voltage on and leaving it on. If you do that, a current will establish in the circuit. The integral of that current is the charge. When you develop a charge that eventually reaches a final value and settles. And this is exactly the kind of response we would see if you look at the charge. Now let's look at an impulse response, starting with the mechanical system. In an impulse response, the impulse response of the mass spring damper system is equivalent to first stretch the spring and then let the system go from there, release the mass and let it go from that initial position. Or we simply slap the mass fast and the mass oscillates and eventually stops. Mathematically speaking, that is going to be an initial condition given to the system. That initial condition is the initial displacement in the spring, is an initial energy stored in the spring. So we move the mass, we let the spring stretch or compress. When the mass is still, we let it go and the system oscillates until eventually it stops. So if you look at the impulse response, this is what you should see, a system that starts either from zero if we slap it and let it oscillate, or it starts from a given point if you give it an initial displacement and let it go, and eventually slowly decays to the original equilibrium position at zero. What is dissipating this energy is again the damping. Why do we see oscillations? Because of the potential energy in the spring being transferred to the mass and back to the spring. So potential energy in the spring goes to the mass as kinetic energy and back to the spring. But in that process, the viscous friction coefficient due to that damper dissipates a little bit of energy, so these oscillations eventually die out. Looking now at the electric system for its impulse response, again, let's assume that there is an initial voltage in the capacitor or there is an initial current in the inductor and you let the system go from there, we'll see the same sort of response. Eventually, there is no charge in the circuit. Now let's take the same example once again, but now instead of looking at the displacement, let's look at the speed. And instead of looking at charge, let's look at the current. Let's start with the step response. So if you turn the circuit on, we'll see initially a current flowing in the circuit, and eventually the capacitor becomes an open circuit and the current goes to zero. Let's look at the step response of the mass spring damper system, but now again our output is the speed. If you apply a force to the mass and hold that force constant, the mass will start to move, so the velocity changes, the speed changes, and when the system reaches equilibrium, the speed tends to zero. So you're going to see exactly the same behavior. Now let's look at the impulse response. Turning the circuit on and turning it off very fast, or letting the circuit go from an initial condition in the capacitor or in the inductor, will make the current eventually settle to zero. If we have now the mass spring damper system with initial compression in the spring and let it go from rest, it will also oscillate and eventually settle to zero. So we see that the impulse response for these two systems are exactly the same when we consider the input V and F, and when you consider the output to be I and V. And here is a summary of these observations. The displacement and the charge will follow the same temporal response. The velocity and the current will also follow the same temporal response. This first graph here is the step response of both systems. In the second, the impulse response for both displacement and charge and velocity and current is also equivalent. We see again that because the systems have the same second order structure, the differential equation that describes them has the same structure, we can make this analogy between the displacement and charge, between velocity and current, and between the elements that constitute these systems. If you now have a mechanical system but you prefer to solve an electric system instead, or if you're more comfortable with mechanical systems rather than an electrical system, we can always switch between them. We can always create an equivalent electric circuit for a mechanical system or an equivalent mechanical system for an electric circuit, because the differential equations that I described them are exactly the same. There are a few exercises in this lecture to help you practice how to find the differential equations for mass spring damper systems and for the electric systems. They will be posted in a different video. I recommend that you attempt each of these exercises on your own and then check the answers with the annotated PDFs. And if you have any questions, please do watch the separate videos that will be posted for each one of these exercises. Thank you.